Hello, welcome again to the amazing world of chemistry, right? Right, so in this video we're going to look at the solubility product constant. And so then this is going to be part, I think it's like 8 of the solution equilibrium. And so when we're looking at solution equilibrium, we're looking at a thing called KSP, solubility product constant. And the whole point for solubility product constant, see, I think I got a little bit of stuff up here. Yeah, it is part 8. The whole point for solubility product constant is that we have these things that we say don't dissolve, like AgCl. We say they're insoluble. Well, it turns out they actually are soluble, but very little, so we can still say they're insoluble. But the reality is that some of this actually comes off of this and goes into solution, but a very, very small amount. So how do we express that? Well, we use a KSP expression, and a KSP expression takes the concentrations of each of the products and multiplies them by each other. And the KSP expression is written from the balanced equation of the dissolution of whatever the salt is, and the exponents in the KSP expression come from the coefficients in the balanced equation. So in this one, you know, this is a 1-to-1. This just has two things. It breaks up into two things. So in this case, our KSP, if we were going to get this down to a value of x, say I wanted to solve for the amount of silver ions, or say I wanted to solve for the amount or the moles of AgCl that dissolve right here, because that's going to be a value of x. And then this is going to be in value of x. So KSP equals x squared for this one. Now it gets a little bit more complicated when you, but not much, when you go up to one that has a little bit higher amount of ions from the original formula unit. So here we have lead chloride. So lead chloride breaks up into 1 lead and 2 chlorines. Right? So the solubility product constant for this is going to have the concentration of lead times the concentration of chlorine ions, and that's going to be the second power, because the KSP expression takes the coefficient from the balanced equation and uses them as exponents. So the KSP is equal to lead times chlorine squared. Now, how do we solve then for x? If we want to solve for x, remember this would be x, this would be x, this would be x. Well, just like we've always done for substituting in x, we can do an ice table to find out the value of x. So if we look at this, the value of x, we're going to be subtracting from here with our change. We're going to be adding to lead, and we're going to be adding to chlorine 2 times, right? So we have 2x because chlorine is double. And so then our final values is 2x for chlorine and x for lead. And so what we do is we just insert our ice table values into our KSP expression in place of our names for our actual ions. So we put them in there. And then this remains here because that's part of the expression. And so what we have is x times 2x squared. So if you were to multiply that out, you end up with 4x cubed. Now they can even get greater than that, because as you know, some salts can break up into 3 or 4. I mean, so 4 particles, and then some, in this case, is breaking up into 5 particles, right? So look at the one with 4 particles. Now, lanthanide chloride, it breaks up into the lanthanide ion and then 3 chlorine. So our KSP is going to be x times 3x to the 3rd power, right? And so if you take 3x to the 3rd power, you have 27x cubed. Multiply that times another x, 27x to the 4th. So you could even do that with something bigger like calcium phosphate. So calcium phosphate ends up, its balanced equation as 3 calcium ions plus 2 phosphate ions. So our KSP is going to have this one squared, and then, or this one cubed, and then that one squared, right? And then our ice table is going to give us a value of 3x for this one and a value of 2x for that one if we wanted to solve for x. And so our total is going to be, our KSP, if we mash it all together, is going to be 108x to the 5th. So how do we use that? So let's go ahead and use that. So let's say we had an equation where we had molar solubility. Let's say that we said that the molar solubility per mole of this was 1.8 times 10 to the negative second. So what are we saying? We're telling you x, really. So this is the value of x, because for every 1 mole of this that dissolves, we're going to get 3 pieces, 3 particles. We know that our KSP, in this case, our KSP equals then lead, and that's 1 times bromine, and that is squared. And then our ice table is going to put our values in there for lead as just being an x, and 2x for bromine, and so our total is going to equal this, 4x cubed. So we can actually solve for the KSP here if we want to, because we know the value of x, and that's our only unknown. And, well, it's one of 2 unknowns, and so now we only have 1 unknown left. And so we throw that in there, and that, of course, is going to be taken to the 3rd power and then multiplied by 4. If you take that to the 3rd power and then multiply by 4, let's see, run that through the calculator real quick, you should get 6.57 times 10 to the negative 6 is what I got on that. And so then that is actually the KSP. So that's what we just calculated KSP from molar solubility. And so that's one kind of practical way of using this expression right here. So let's do another one real quick. What if I started with mass? What if I just started with a certain amount mass of zinc phosphate? Now zinc phosphate is one of those fun ones because look, it has 5 ions that are going to dissociate. And so if I take grams of this and dissolve it in a liter, what's the KSP? Well, I'm kind of one step back now, right? Because I'm starting with grams, and the step before we started with moles. And so we're just going to have to get to that point. So we have to turn this grams into moles. And so we have to divide by the molar mass of the zinc phosphate. So add up 3 zincs and 2 phosphates and 8 oxygen, and you should get 386.17. So divide that, and we find out that we have this many moles, and it's actually a molarity because we found that it was dissolved in 1 liter. So it's our molarity as well. So now we know our molarity of our original salt, and that's going to be the value of x in our equation, because this 1x breaks up into all the other ones. And then we remember that the KSP for something like this, just go back here so I don't have to write it out again, looks like this. It actually is the value of 3x cubed times 2x squared, so we end up with 108x to the 5th. So then all you're going to do is you're going to take your x number right here that you found, insert that right here, take it to the 5th power, and then multiply it by 108, and you should get an answer. We'll round up to 9.00 times 10 to the negative 33rd. That's what our KSP is for that bad boy. All right, so there's lots of ways to get here, and so here we just started with grams, and we found that we were able to dissolve exactly this many grams in a liter of water. So that's how they find the KSP, actually. So they just get the exact amount of grams and then do this process right here, and there you go. You got your KSP values, and like I said, these are listed in the backs of your book. Let's try one more example real quick with KSP, and then we'll be done with this kind of idea. So how about the solubility of a buffered solution in grams per liter? Now you always got to make sure you know what they're asking you. Are they asking you for molarity? Are they asking you in grams per liter? So this is kind of a density idea. They could be asking you for all sorts of different things, and so you need to be able to recognize that and then solve the problem accordingly. So with all of these equilibrium, it's really about knowing the chemistry, what's going to happen, and then the calculations are not so hard after that. So here's what we know. We have a pH of 9.9. Our salt is manganese hydroxide, and we could look the KSP up in the back of the book, and we find that it's 106, or not 106, 1.6 times 10 to the negative 13th. So our KSP expression is going to be this, breaking up into 1 manganese and 2 hydroxides. And so then that's going to give us a KSP of, what's it going to be, 4x cubed. At this point, what we're going to need to do, though, is we have our KSP, and our pH actually could tell us this right here. So we essentially have our hydroxide ion concentration, we have our KSP, and so then all we're left with is to solve for our concentration of manganese. So, and the concentration of manganese would also be the concentration of the molar concentration of the salt, because it is value of X as well as Mn. So let's go ahead and work this out. So our first step really is going to be to figure out then what is our concentration of hydroxide ions. So our pH is 9.9. So let's go ahead and turn that into a concentration well, actually, this is not our pH, or our pH is this, but what we need is a pOH, because we're looking for our hydroxide concentration. Remember, pH is the concentration of hydrogen ions, the log of that, negative log, and then the pOH is the concentration, the negative log of the concentration of the hydroxide ions. So to pOH, remember, equals is going to be 14 minus the pH, or the pOH. So so 14 minus 9.9 is going to give us our pOH, and so that's going to equal 4.1. So 4.1 is our pOH. Now to turn that into concentration, we'll take the antilog of that, so antilog of the negative pOH. So the antilog of negative 4.1 is going to give us something like 7.94 times 10 to the negative 5th. All right, so here is our concentration of hydroxide ions, and we know our KSP, so now I guess all we really have to do is start plugging stuff in. So we have 1.6 times 10 to the negative 13th is going to equal the concentration of Mn times the concentration of hydroxide ions, which we know is 7.94 times 10 to the negative 5th, and that's squared. So then to solve for this, you just divide 1.6 times 10 to the negative 3rd by 7.94 times 10 to the negative 5th squared, and you will get our Mn concentration equals 2.54 times 10 to the negative 5th. Now, actually, the question's probably going to ask you for pH. No, actually, no. The question isn't asking for pH. Where's sulfur? The question is asking grams per liter. So here we have a molar concentration. So this is the amount of moles, and so what do we do from this point? If we know the amount of moles, it's pretty simple to find the actual amount of grams, because then all you have to do is multiply it times its molar mass. So to calculate the molar mass, we're just going to have to take this and add it to 2 oxygens and 2 hydrogens. It's going to come out to 88.938. If I multiply that, I'm going to actually find the amount of grams I have here. So 0.0023 grams, and this was all in a liter. So it is 0.0023 grams per liter is the exact amount of this in buffered, to make a buffered solution of a pH of 9.9. So handy information. Seems like a lot of calculations and work, but you really found out a lot of information from very little information to start with.